Okay, so today we're talking about simple machines. Simple machines are devices that make work easier to do. The same amount of work gets done when a simple machine does work or when something else does work. And as we've already talked about, work is force times distance. So in that equation, force times distance equals work. If I need to get the same amount of work done, but I want to put less force into something, then how mathematically do I get the same amount of work done with less force? The equation is work equals force times distance. What can I do in that equation to get the same amount of work done, but put less force in? Blank answers. Okay, let's try that again. Let's do it this way. 3 times 4 is 12, right? Let's say that 4 is my force value. I'm pushing on something with 4 newtons of force. And I push on that something with 4 newtons of force for 3 meters. So I've done 12 joules of work. Let's say I still need to get 12 joules of work done, but I only want to push on this thing with 2 newtons of force. How can I have 2 newtons of force do the same amount of work as 4 newtons of force if I still need to get to 12 joules? 2 times what is 12? 6. So if I push on something with 4 newtons of force for 3 meters, I've done 12 joules of work. If I push on something with only 2 newtons of force, and I can push on it with less force for more distance, 2 times 6 meters, I've still done 12 joules of work. The idea of a simple machine is to take a certain amount of work that you need to get done and push on it less, do less effort, less force. But you have to do that less force for a greater distance. And then when you do that, you get the same amount of work. So simple machines are devices that magnify the amount of force you put in and get a greater amount of work done than you would normally be able to do with that small amount of force. But the trade-off is you have to do that less amount of force for more distance than you would have done otherwise. Okay? So here we're going to be looking at the kinds of simple machines. There are a couple of classic simple machines. There's most people say that there are 6 simple machines. There's really only 3 broad categories, but we're going to show you the 6 kinds of simple machine. The first one is a lever. A lever is a bar which does work because of forces applied at another point. So the resistance arm is the part of the lever that does the work, and the effort arm is where you push on it, right? And then the fulcrum serves as the pivot point in the middle. So here, let me grab a ruler, and I will say that it is my goal to raise this load a certain amount of distance. If my fingers are the fulcrum and I push over here, this is the effort arm. I'm pushing here, and my load is rising over here, and my finger serves as the fulcrum. So this is a lever, right? Think of like a crowbar. You're pulling a nail out of a board, or a pry bar to get a rock out of the ground, or a catapult to fling something right a long ways away. These are all levers. Pair of scissors, pair of pliers, lots of joints in your body have levers. So a lever is anytime you have a stick, a bar, something rigid, and a point of pivot, and then a load and an effort. Now there are 3 ways you can arrange this. You could have what I've been demonstrating, a first-class lever where the fulcrum is in the middle, and the resistance is on one side of the fulcrum and the effort is on the other. This is a first-class lever, okay? The fulcrum is in the middle. Second-class lever, the resistance is in the middle. So the fulcrum is at one end, the resistance is in the middle, and I manipulate my load like this, okay? This is like a pair of a nutcracker. If you guys ever eat walnuts, you squeeze on the handle, you put the nut in the middle, and the nut gets crushed, but the fulcrum is on the outside. A nutcracker or a garlic press would be the same kind of idea, okay? A wheelbarrow is this as well. The wheel is over here. The bucket full of rocks is in the middle. Handles are at the end. Second class lever. The load or the resistance is in the middle, okay? And then the effort arm in the middle is where you have the fulcrum on one end the load on the other end, and you lift here. Okay, the effort is in the middle. This is like a pair of tweezers, where you've got the two parts of the tweezers and they meet in the back, and you squeeze in the middle, and then you're pulling out the splinter or plucking your eyebrows or whatever at the end, right? Okay, so those are the three classes of lever, and if you remember what's in the middle, first class, second class, third class, put them in order in your brain, 1, 2, 3, and then F-R-E, it's kind of like the word free, only there's not another E at the end of it, right? So I remembered that a lever makes me free to do less work. That's how I remembered this. A lever makes me free, lets me be free to do less work. F-R-E, I forget the last E. And then that helps me remember fulcrum in the middle, resistance in the middle, effort in the middle, for which one is first, second, or third class. That's my little brain thing for how I memorize the orders. Okay. Okay, so this is a first class lever, fulcrum in the middle, force at one end, load on the other, or resistance on the other. A seesaw is an example of that. This is a second class lever. I'm sorry, just kidding. This is a first class lever as well. Fulcrum in the middle, load on one end, effort on the other. Okay. This is a first class lever. The effort is over here, the fulcrum is in the middle, the load is at the other end. This is a first class lever. Effort on one end, fulcrum in the middle, load on the other end. Okay, these are all first class levers. Second class lever, fulcrum at one end, load in the middle, and then the force at the other end. So here we have a wheelbarrow, the load, the fulcrum, the effort arm. And you doing push-ups, fulcrum, effort, load. Third class lever, fulcrum at one end, force in the middle, load at the other. Okay, here we have a pair of tweezers. Or chopsticks. There you go. Chopsticks is another example of that. A bat, fulcrum at one end, effort in the middle, resistance out at the other end. Most of the joints of your body are third class levers. Most of the joints of your body are third class levers. The fulcrum is here at the elbow. The muscles attach just off of the elbow. And then the load is way at the end. So fulcrum, effort, load. Most of the joints of your body are third class levers. Okay? Take a moment, write that down. So, why do you get better results on a big lever than a small lever? Why do you use a big, large wrench to turn a big bolt and not a little wrench to turn a big bolt? We have to do something called the law of torque. So when you're looking at levers, the force that you apply to a lever, it means more the further away you are from the fulcrum. The amount of force that you apply to a small lever very close to the fulcrum is not going to be magnified very much by the lever. But if you get a very long lever and you can apply force to the end of that, then you're going to get more production out of your simple machine, out of your lever. That has to do with something called the law of torques. Torque is a term in physics that has to do with the amount of rotational force that you can apply to something, and it has to do with how much force you apply to the lever and how far away from the fulcrum you apply that force. So if you're trying to lift a big rock out of the ground and you walk over there with a screwdriver and you put it in the ground and you pull on the screwdriver, you might bend the screwdriver before you lift the big rock out of the ground. But same big rock, you walk over with a pry bar that's 6 feet long. You stick it in the ground next to the rock and you grab the top of a 6-foot pry bar. It's going to be very easy to lift the rock out of the ground because you're applying that force further away from the fulcrum, and it gets magnified. So the amount of force is the amount of rotational force that the object feels. It's a product of how hard you pull and how far away from the fulcrum you pull. Force times effort. I'm sorry, force times distance. Now, in a lever, you have the point of fulcrum, and you have two sides of the lever. You have the side that has the load and the side that has the effort. And because the lever is rigid, whatever torque you generate on one end gets passed to the other side of the lever. And so you have the force times distance on one side of the lever is going to generate a certain amount of torque, and that same torque product is going to be carried into the other side of the lever. So you have force and distance on both sides of the fulcrum. Okay, which is why you want usually a short resistance arm and a very long effort arm. So you can put a little bit of effort in on a long arm to the fulcrum, and then have all of that torque turn into force a very short distance from the fulcrum, and apply a lot of effort to the load. So let me show you pictures of what I'm talking about here. Okay, this laborer is told to move a 250 kilogram rock off of a path. Move the rock, Bill. He uses a pry bar to get it done. If he has a 2-meter pry bar and he sets a fulcrum at 25 centimeters from the end of the bar, so that's that wheel of wood there that he's using as a fulcrum, and that's 25 centimeters from the end of the bar. How much force does he have to apply to the end of the pry bar to move the rock? He's got a 250 kilogram rock. That's a stinking heavy rock. That's almost 600 pounds. Okay, big rock. He's not going to be able to raise it with just squatting and picking it up. But we need to see how much force he has to apply at the end of this long pry bar to get the rock to move. So here's what we do. There's the effort arm, there's the fulcrum, there's the load. Okay, and the distances I gave you, it's a 2-meter bar. He's got the fulcrum set 25 centimeters from the end. So the resistance arm is 25 centimeters, 0.25 meters. The effort arm is 1.75 meters, right? 2 meters in total, 25 centimeters of it here, 1 3/4 meters of it left. Okay, we need to calculate the force of gravity on the rock to know the force that the rock is being held down with. So 250 kilograms times the acceleration of gravity, F equals ma. That rock has a downward force because of gravity of 2,450 newtons. It's a lot of downward force that he has to overcome to get the rock to move. Okay, so now we're going to use the law of torques, and we're going to say, okay, this rock, this is the resistance force, right? The resistance force, 2,450 newtons. The distance of the resistance arm is 25 centimeters, 0.25 meters. And then we're going to have a distance of the effort arm of 1.75 meters. And then I'm going to figure out how much he has to push back here to cancel out the downward force of gravity on the rock. Okay, so put those numbers in. This you can just multiply. 2,450 times 0.25 is 612.5 joules. Newtons times meters. Okay, and then over here, that 1.75 meters and the force, that's what I'm solving for. So I need to divide both sides by 1.75. And I get a force on the effort arm of 350 newtons. So he only has to push, oops, just kidding. He only has to push with 350 newtons of force at the end of the pry bar for the rock with 2,450 newtons of downward force to move. So you can see the benefit of a simple machine here. He's doing the same amount of work. Both sides of this equation equal the same amount of joules, 612.5 joules. But over here, he's doing that much work a lot easier than if he hadn't had the tool. You understand what's going on? Okay, there you go. Go ahead and write that part. Okay, so two more simple machines that are very much like levers. One is called a wheel and axle, and one is called a gear. And so cars have both of these kinds of simple machines. For a wheel and axle, you do a certain amount of work on the axle, and then the wheel magnifies that work. Okay, so when you're driving down the road in a car, the engine might be turning the drive shaft 2,500 times per minute, average freeway speed on an engine. 2,500 rotations of the drive shaft, or of the flywheel, sorry, on the engine. But the transmission is going to take that 2,500 rotations per minute of the flywheel and magnify that to something more like 5,000 or 6,000 rotations per minute. And the transmission is doing that by using gears and multiplying the spinning of the flywheel to multiple spinnings of the drive shaft that goes back to the wheels. And the reason it can do that is because there are gears of multiple sizes. And so gears that interface with teeth are kind of like levers, where a bigger wheel is like a longer effort arm, and a smaller a smaller wheel with teeth on it is like a smaller lever of the axle. So if you have a big wheel with teeth and a small wheel with teeth, the small one is going to turn a lot more times for every one rotation of the big one. So it's just like a lever. More force on this one gets multiplied on the smaller one. Same concept, same ideas of multiplying the force, but having to do it for more distance, right? Gears are like that. So the engine is turning, the transmission uses gears to multiply the number of rotations per minute. So now your flywheel on your engine is turning 2,500 times a minute. The drive shaft might be turning 5,000 or 6,000 times a minute. And then that goes out to the wheels, and the wheels are going to take that 5,000 or 6,000 times per minute and do that same number of rotations, but instead of being as big as your axle, it's now as big as your tire. So the tire is still going to turn that larger number of times per minute, and it's going to get a lot more distance down the road because the wheel is big. So it represents more distance being done. So wheel and axles multiply force with the ratio between the radius of the axle and the radius of the wheel. Gears can do that, and then you can also put two gears together and multiply force by the ratio between the different radii of the gears. So let me show you some pictures to help you understand this. So here is a wheel and axle system that's used to draw up a bucket out of a well. Okay, so you could just lean over and pull the bucket up and work against gravity directly. But if you put a wheel and axle above it, which most old school wells had, then your resistance is only rolling the rope up along this fairly narrow diameter. But your effort is this big long-handled wheel out here that you use to turn. So you get to take a greater distance around, which means a lot less force is required than this distance around. So you're pulling up this heavy bucket full of water, but it's very easy to turn this wheel and draw it up. It's a lot easier than if you just were to grab the rope yourself and pull it out of the water. Okay? So the ratio in diameters from the axle to the wheel is just like a lever. And on your bike, there are lots of examples of this, right? So you have a long arm on your pedal and a shorter distance on the sprocket. So this is a wheel and axle kind of system. You're putting in your force to a long force arm, and the resistance is a short resistance arm, or at least shorter resistance arm. And then the chain goes through a gear system. So now the distance here, I'm putting my force into a larger effort arm, and the resistance arm back here is a lot smaller. So again, it makes my work easier. And now for every rotation of this pedal, I'm getting 5 or 6 rotations of this little sprocket back here. So I'm magnifying my distance, which makes the work easier. Okay, with the force less. But then the wheel itself is another one of these systems where I have a small effort arm and a large resistance arm. So this is a third-class lever, which goes back to the wheel. So now every rotation that I get out of this, I get a lot more ground covered by the size of the tire, because I can easily make this gear spin around. But if this is all the bigger my tire is, every time I spin that gear around, I'm only going to go like 6 inches across the ground. So now by having a big tire, every time this turns around, I get, maybe 4 or 5 feet of ground coverage when the wheel turns. So wheels and gears are a type of type of lever. Okay, so pulleys are the next broad category of simple machine. Wheels, axles, gears, levers, that all works kind of the same. Pulleys are different. Pulleys reduce the force needed to do work based on the number of rope laps in the system. So every lap equals one magnitude of mechanical advantage. So the reason that works is if I've got a 100-pound weight here, and I've got 2 laps of the rope in this pulley system, when I grab the rope and I pull, this piece of rope is holding half the weight, and this piece of rope is holding half the weight. So this 100-pound weight is being supported by 2 ropes, and each of those ropes holds 50 pounds of the 100-pound weight. And so it's only the force of this rope that goes over the pulley that I'm pulling on that I have to account for. This 50 pounds is fixed. So I'm able to lift a 100-pound thing by pulling 50 pounds of force if there's 2 laps of the rope. And the more times the rope passes between one pulley gang and the other pulley gang, the less force I need to put in to get the thing to raise, because it's being supported by every lap of the rope. So the mechanical advantage here is 2, 1 mechanical advantage multiplier for every pass of the rope. So some of these rope systems get really complicated, and especially if you've ever been on a sailing ship, that's where you see a lot of these pulley systems in use. If you've ever been sailing, sometimes you'll look up and you'll see tons of ropes going up to the same part of the sail. And that's because by having lots of laps of rope go up to that sail, a sailor can pull relatively easy against this huge piece of canvas that's got all this wind on it. There's a lot of force on that sail. In order to move that sail, you've got to overcome the force of all the wind on that sail. You'll never do it if you just grab the canvas and walk. It'll flick you off the boat. So by having lots of passes of a rope on a pulley system, the sailor can move the sail easily. Okay? So this is another example. If I'm going to pull on this rope, I'm only having to bear the weight of this lap of cord. But there are 1, 2, 3, 4, 5 laps of cord. So this weight, I'm only experiencing 1/5 of the weight of that thing as I pull on. Okay, so mechanical advantage, just count the number of laps of the rope, and it'll tell you how that works. Here's a really good diagram where I have a 1 kilogram mass, and if there's a pulley at the top and it's just 1 lap of rope going down to the resistance, then a 1 kilogram mass and a 1 kilogram mass balance each other. But over here, I have 2 laps of the rope, and so 1 kilogram mass balances a 2 kilogram mass. Here I have 3 laps of the rope. No. And so a 1 kilogram mass balances 3, a 1 kilogram mass balances 5, a 1 kilogram mass balances 6, depending on how many laps of the rope there are. Okay? So you see there's a lot of the same. The last simple tool is an inclined plane. Okay, and I'm just for the sake of time, I'm going to keep talking while you write. An inclined plane, or a ramp, gives you a mechanical advantage based on the ratio of the length of the ramp to the vertical rise of the ramp. So if you've got this wheelchair ramp here, you could take somebody in a wheelchair and park them next to the van, and then get in a good lifting posture, wrap your arms around the wheelchair, and say, "Hold on, Charlie," and grunt and sweat a whole lot and set the guy in the van. Okay? You're doing a certain amount of work by raising Charlie and his wheelchair this distance. You could just squat him. Yeah, Charlie, sure, why not? Why not? So you could just squat and lift Charlie and his wheelchair and put him in the van. And that's a certain amount of work. Or you could get the exact same amount of work done by getting a ramp and pushing Charlie and his wheelchair up the ramp. Now you have decreased the force, but increased the distance. If you just squat Charlie in his wheelchair, you've only got to raise him about 8 inches. And he's in the van. Do it over a ramp, you got to push Charlie in his wheelchair like 6 feet. But by multiplying out the distance, you have decreased the force. And so a ramp is a simple machine. An inclined plane is a simple machine that multiplies your force, but increases the amount of distance you have to do that force. Okay? There are lots of ways to use an inclined plane. A ramp is one of them. There are others. I'm going to go to these pictures. A couple of you are still writing. I'll go back to this one when we're done. Wedges and screws. I thought it was done. Okay. Oh, just write down that wedges and screws are modified ramps. Just put that down. Wedges and screws are modified ramps. Okay. And I'll show you a picture of that. Wedges and screws are modified ramps. So here we have a splitting wedge. This is a board that you need to rip in half. You could just take your fingers and find lines of the grain and like dig your fingers in and go and rip the board in half. Yeah, if you're strong enough, you can do that. Or you can use a wedge and you place the tip of the wedge in the board and you start hammering. And now you're still only going to spread the board this far. This is the work, spreading the board that far. But now you can spread the board that far, but you have this far to get it done, right? You've got a lot further to spread that work out, so it becomes easier. Splitting wedges just take that amount of work and let you to spend a longer distance to get that amount of work done, okay? If you've ever been lumberjacking, those things are very useful. Out here where you don't burn firewood, I don't know why you would have done that. But in Flagstaff, where I used to live, did that every fall to get ready for the firewood you need for the winter. Here's another example, a doorstop. I jam up a door so it doesn't open by lifting the door and binding the hinges. So the hinges can't work because there's too much pressure on the hinge. So though I could just stand there and lift the door and jam up the hinge and then stay there forever holding the door open, which is a great way to do it. Or you put this little thing there and you have distance over which to jam up the door, and then a nice little handy thing about all the tension that you've created is it stays there. So that's nice. This is another just example of an inclined plane. Okay? A screw is just an inclined plane. If you were to imagine unwrapping a screw, you start down here and you unwrap that thread, what you wind up with is a really long ramp that's been wrapped around the screw. And so this is a very long inclined plane that has been wrapped around a central thing. And then when you put a screw in a piece of wood, you're wrapping this inclined plane into the grain of the wood, and you're creating a whole lot of tension that you could never create if you just pushed the thing in the board. But because the inclined plane takes so much distance to get that work done, it's very easy to drive a screw. Okay? And then I think I got one more picture. No, that's it. Okay. So wedges and screws are kind of inclined plane. Any questions? All righty.